how do you measure something you can't even see? A change so small it's, well, practically non-existent. Today, we're going to dive into an absolutely ingenious piece of physics that does just that. It's an invention so profound, it actually helped reshape how we see the universe by turning the invisible world into something we can literally count.
I mean, seriously, think about it. This is one of the biggest challenges in all of science. We know stuff is happening on a microscopic level all around us all the time. But how do we quantify it? How do you put a number on a change that's thousands of times smaller than a single human hair?
For instance, take a metal rod. If you warm it up by just 1 degree, it gets bigger. It expands. Now, not by much. We are talking about a change on the scale of atoms, but it's a real physical change. So, how on earth do you build a ruler that's precise enough to measure that?
Or what about this? The air in this room. Light zips right through it, but the air itself actually bends that light path, just ever so slightly. It's another one of those real physical effects that's so subtle it feels like it should be totally impossible to measure.
It sounds like some kind of magic trick, right? But it's not. Physicists, being the clever people they are, developed an incredible tool specifically for measuring the unseen.
And this is it. This is the solution, the Michelson Interferometer. Now, at first glance, it looks pretty simple, right? It's just a laser, a few mirrors. But this simple-looking setup is one of the most precise measurement tools ever invented, and it's all because of how it cleverly plays with light.
So how does this thing pull it off? Well, the secret is in what I like to call light's interference trick. It's all about making light waves do the hard work for us.
Okay, so let's trace the journey of a single beam of light. First, it hits a special half-silvered mirror called a beam splitter, and, just like the name says, it splits the beam perfectly in two. Each of those new beams now travels down its own separate path, or arm. Then, at the end of each arm, a mirror bounces the beam straight back where it came from. Finally, the two beams meet up again, right back at that beam splitter, and they're sent off together towards a screen.
And here is where the magic happens. When those two light beams come back together, their waves interfere with each other. It's just like when ripples cross in a pond. If the peaks of two waves line up, they get bigger. They create a bright spot. But if a peak from one wave meets a valley from the other, they cancel each other out, and you get a dark spot. The result is this beautiful, clear pattern of bright and dark bands. We call them interference fringes. In this pattern, this is the key to everything. It's our visual readout, and it is unbelievably sensitive. The slightest, and I mean slightest, disturbance to either one of those light beams will cause this entire pattern to shift.
So, if this pattern is so sensitive, let's put it to the test. Remember that first challenge, trying to measure how much a column of air bends a beam of light? Let's see how the interferometer handles it.
This setup is actually pretty straightforward. We take a small sealed container, an air cell, and we just place it in one of the interferometer's arms. So now, one of our light beams has to travel through this little pocket of air, while the other beam is still traveling through a near vacuum. Now, the procedure here is just so clever and simple. We start with the cell under a little bit of pressure, and then we just slowly, carefully release that pressure. So, as we let the pressure out, the air inside the cell gets less dense. You can think of it like a hallway that's getting less crowded. It's just easier to move through. For the light beam, this means it can travel just a tiny bit faster. And that tiny change in speed means it gets back to the beam splitter at a slightly different time than its partner. What's the result? We see it directly. Those interference fringes just drift right across the screen. And here's the best part. We don't just watch them drift, we count them. Every time a bright band moves past our little marker, we count it as one fringe shift. And what we find is this perfect straight-line relationship. The more pressure we release, the more fringes shift. By just counting these shifts, we can calculate that invisible property of air, its refractive index. We've literally measured the unseeable. How cool is that? Incredible, right? We just measured a property of air by counting shifting light patterns. So now, let's apply that very same principle to our second big challenge, watching a solid metal rod expand.
For this experiment, we switched things up a bit. We replaced that air cell with our sample rod. And the mirror at the end of this arm is now physically attached to the end of the rod itself.
The action this time? Even simpler. We just gently heat the sample rod. That's it. So, as the rod gets warmer, it expands. We are talking about a microscopic change in its length. Way too small to see or feel. But that tiny expansion pushes the attached mirror forward, ever so slightly. And this is where it all just clicks into place. Just like with the changing air pressure before, this tiny movement of the mirror changes the total distance that one of the light beams has to travel. And that minuscule change in distance is more than enough to cause those interference fringes to shift all over again.
So just how precise are we talking here? Well, the laser light we're using has a wavelength of about 650 nanometers. That's 650 times billionths of a meter. That's the scale of the ruler we're working with. We're not measuring in millimeters or even micrometers. We are measuring with the wavelength of light itself.
And you know, the best part is, the math isn't even complicated. The total expansion of the rod is simply the number of fringe shifts we count, multiplied by half the laser's wavelength. We are literally translating a simple count, 1, 2, 3 shifting bands, directly into a measurement on the scale of nanometers. Amazing!
So when you put it all together, what this device really does is give us a bridge. It's a bridge from the microscopic world to our world. It translates these tiny, invisible events into a language we can actually see and count, literally making the invisible visible.
So what are the big takeaways? What should you remember from all this? It all comes down to this. The interferometer splits light to create this super sensitive reference pattern. Then, any tiny change in the real world, a little shift in air pressure, a tiny bit of thermal expansion, it messes with that pattern. We can then see that disturbance as shifting fringes, and we can just count them to get an exact measurement. It's a brilliant trick for turning nanometer-scale events into something we can just count with our own eyes.
You know, the Michelson Interferometer isn't just a clever tool. It's a testament to human ingenuity. It's really a way of thinking. And that leads to a final, much bigger question. If a simple arrangement of mirrors and light can make invisible expansion visible, what other secrets of the universe are hiding out there, in plain sight, just waiting for the right clever trick to reveal them?